We're focused on right triangle trigonometry. So this means all the things that I give you currently have to do with right triangles. They have to have a right angle in them. I can't use them for any triangle. It specifically has to be a right triangle. You should know the three basic trig ratios. So when I say, every time I say trig, I mean trigonometric. But I'm not going to write or say that every time. You probably don't want to either, right? So the trig ratios. Ratio is a comparison of two values. When we talk about trig ratios, the two values that we're comparing are two sides of a right triangle. Now, you may remember we kind of talked about this at the end of the period after our matrix quiz. We talked a little bit about special right triangles. And so I used the phrases like legs and hypotenuse. And then in a 30, 60, 90 triangle, you have a short leg and a long leg and a hypotenuse. Okay, in a 45, 45, the two legs are the same. When we talk about trig ratios, suppose we have some right triangle and we label some angle theta. We're going to label the sides opposite, adjacent, hypotenuse in relation to theta. Do you remember doing that? Okay. Hypotenuse should be an easy one for you to label. Oops. It's the longest side of a right triangle. It's also always opposite the right angle. When you're deciding between opposite and adjacent, remember that it's relative to wherever theta is placed. So theta is an angle, whatever side it intercepts, that's its opposite side. Whatever side makes the angle with the hypotenuse, that's its adjacent side. Tell your pod members how to do sine, cosine, and tangent. Okay, I hear some really good discussions. I heard a lot of people say right at the very beginning, so, katoa. Yay! So, katoa. It's how you remember what the ratios are, right? So, SOH represents sine, it's opposite over hypotenuse. Ka, CAH, is adjacent over hypotenuse. Toa is tangent, opposite over adjacent. Okay. So I kind of expect everybody in this room to already know those three trig ratios. If you're feeling like really overwhelmed at this point, you don't remember ever seeing that, you probably need to schedule some time before after school to come in and see me. Now I have a little piece hidden over here because I don't think that in geometry you get to what we refer to as the reciprocal ratios. Okay, so what do I mean when I say reciprocal? Flipped. Okay, when you say opposite, I think change signs, right? Plus and minus. When we say reciprocal, we should think about flipping the fraction. So we already kind of know what the reciprocal ratios are going to look like, right? Hypotenuse over opposite, hypotenuse over adjacent, adjacent over opposite. Okay, they're just going to be the flipped versions of sine, cosine, and tangent, but they have new names. Okay, so I'm going to write out the names. They are cosecant, secant and cotangent. Do those look familiar? Did you learn those last year?
You mentioned it.
Oh, some people have heard it mentioned. Okay, great. Some of us are saying, no, I've never heard those before, and then some of us are saying, yeah, that looks familiar. Okay, so remember, just like this, your geometry teacher was probably really specific. There are no sins in geometry, so don't call it sin theta, it's sine theta. This is not cos, it's cosine, right? So they have actual names, those are just abbreviations. Same thing for the reciprocal functions. So I wrote them out so that you could write them down, and now you know what to call them, but these are their abbreviations. Move this up a little bit for you. CSC is going to be cosecant. SEC is secant. And COT is cotangent. So if we want to learn to read and talk like mathematicians, we're going to name those trig functions. I'm not going to call it cot. Cotangent. I don't even know. Someone say the first one then. No. And you could certainly go in and fill in the opposite or the reciprocal ratios. There's the hypotenuse over the opposite. There's hypotenuse over adjacent. And there's adjacent over opposite. Now, tomorrow we'll look at those reciprocal ratios just a little bit differently so that we can do reciprocal ratios in our calculator. Because our calculator doesn't have opposite over hypotenuse and stuff like that. So we'll talk about that more tomorrow. But for today, all you really need to know is that you're flipping the ratio of the two sides. Opposite and hypotenuse becomes hypotenuse over opposite. Okay. Example 1. You can copy the right triangle in your notes. Some of your homework problems tonight are going to ask you, I don't have directions on here, but basically find the 6 trig ratios for theta. So have a little powwow with your group members right now. Tell them what are you going to do so that you can get the 6 trig ratios for theta. And then you can work on it. I don't get theta. Oh, theta is confusing us?
Well, can you just spell it out for me?
Yeah.
Is it Greek letters?
Sorry, I forget sometimes what you do or don't see in geometry.
Well, I remember seeing it actually when I spelled it.
When I draw theta on the board, it won't look like when I type theta. It looks like a 0 with a line through it. When I draw theta, you'll see a squiggle on my O. I just make it like a cursive O. So that it doesn't look like 0, it looks like something else. Yeah. It's just a Greek letter, but it's our stand-in for our angles. So in algebra and calculus, theta usually represents an angle. Just standard one. Thank you so much for asking that question. Make sure that you stop me again if there's something that we're missing from geometry to algebra, because I sometimes forget about those things. I heard a lot of groups, just real quickly, talk about finding the missing side. How will you find the missing side? Okay, Pythagorean theorem. So if you haven't already with your group, go ahead and find your missing side, right? You're going to need to know all 3 side things.
trig ratios. Oh yeah, they are the ratio of the two sides or ratio. Here.
Yeah.
I wrote the same thing twice.
yeah.
Oh, it's fine. My brain's broken.
Is your missing side the square root of 33?
Yes.
Once you find that missing side and you have all three sides to a triangle, you're ready to create the 6 trig ratios. So remember back on that previous slide right above in your notes. So, ka, toa, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. If you're the kind of person that likes to label those, label. Here's my hypotenuse, 7. It's my longest side. The side opposite of theta is square root 33. And the side adjacent to theta, making the angle with the hypotenuse, is 4. Some people label them like AOH. Fine. Cool. Okay, so sine would be square root 33 over 7. Cosine would be 4 over 7. And tangent would be square root 33 over 4. If you ever create a fraction that could be reduced, you should reduce it. Now these, they don't reduce, like 4 over 7, they don't have anything in common. But if you had like 3 over 6, make it 1/2. What should we do then for the reciprocals? Cosecant, secant, cotangent. Just flip them. 7 over square root 33, 7 over 4, and 4 over square root 33. What might we say about a couple of those? Yeah, someone said it. Rationalize those denominators. I'm kind of running out of room, so I'm going to slide everything over. You bear with me here. Get that closer. Okay, rationalize the denominator for cosecant, rationalize the denominator for cotangent. We still want to write things in what we would call like a simplest form or proper radical form. So we got to rationalize the denominator. I'd multiply by the square root of 33 on the top and the bottom. So that's going to be 7 square root 33 over 33. Because the square root 33 times the square root 33 will be 33. And then down here we'll get 4 square root 33 over 33. Okay, so really important, no decimals. Don't use your calculator, don't give me a decimal answer, I don't want it, I want it exact. You guys are taking concept check. If you check your gold sheet and the sideboard on Wednesday, there's going to be questions similar to this. It will say no decimals. Don't use your calculator. Anybody got any questions on 6 trig ratios? I mean, the thing with the reciprocal ratios that you really need to focus on is like learning the names and how to say them, but they're not really too much terribly more difficult. Usually if you have one radical as a side length, you're going to have a couple things that you need to rationalize at some point. Okay, but other than that, if you don't have all radicals, you'll be okay. Okay, new type of question. In a right triangle, theta is an acute angle, so it's not the right angle, it's one of the other two. And the sine of theta is 3/7. Evaluate the other 5 trig ratios. So I'm going to let you brainstorm with your group. If you know that the sine of theta is 3/7, what can you do to get the other 5 ratios? Cosine, tangent, cosecant, secant, cotangent.
Change
Give me some ideas from the groups. What do you think is a good plan if we're trying to find the other ratios? Find the missing side. So you essentially are already picturing a triangle. So, you know, your geometry teacher probably said this to you over and over again. Draw a picture. Draw a triangle. Yeah, do that. It does not matter what your triangle looks like or where your theta is other than one of the acute angles, right? If you have a different looking triangle than me, yours is flipped, totally fine, nobody cares. Okay. What matters is when you decide to label the sides, because the sine of theta is 3/7, we know that the opposite side is 3 and the hypotenuse is 7. And I heard some groups say Pythagorean theorem again. So we're going to do 7 squared equals 3 squared plus x squared. That's 49 equals 9 plus x squared. So x squared equals 40. What should we do with the square root of 40? Simplify it first. Okay, so square root of 40 is really the square root of 4 times 10, which is 2 radical 10. Yeah, I would use this reduced one. Otherwise, you'll put it into a fraction and still need to reduce all the square roots of 40. Okay, so that makes my cosine 2 square root 10 over 7. And that makes my tangent 3 over 2 square root 10. And what will I do with that tangent value? Rationalize. When you have like something in the denominator like 2 times square root 10, you only need to multiply the top and bottom by square root 10. Okay, so this is going to equal 3 square root 10 all over, now it's going to be 2 times 10, which is 20. If you choose to multiply by 2 square root 10, all that means is that you'll be able to reduce your fraction at the end. So if you want to do the least amount of work possible, only multiply by the root. And then looks like I'll have to simplify my secant as well, or rationalize my secant. That's going to be 7 square root 10 over 20. Okay, and you know me, I always like to work smarter, not harder. So if any of my original ratios had been rationalized, I do not flip the rationalized version because that means that I'm going to have to rationalize again. We already rationalized tangent, 3 over 2 square root 10. So the easiest way to get cotangent is to flip it before it's rationalized. Put 2 square root 10 on top, 3 on bottom. and I don't have to rationalize it. If you flip your final answer for tangent, if tangent of theta is equal to 3 over square root 10 over 20, then your cotangent of theta is equal to 20 over 3 square root 10, and you multiply by the square root of 10, and you get 20 square root 10 over 30, which simplifies to 2 square root 10 over 3. That's a heck of a lot more work, right? So, it's smarter, not harder. Anybody got any questions for me? What's that?
I was just joking. I was like,
Which one's the opposite side of Jason's?
Oh, from,
I think you switched it. Like the time before.
well, here's my theta. Does your triangle look just like mine? Okay. So here's my theta, and then, of course, like, this is my hypotenuse because it's opposite the right angle, right? When you're looking for your opposite side, it's whatever side you intercept when you, like, open up the angle. So 3 is opposite. The side that makes the angle with the hypotenuse, that's your adjacent side. Okay. Now, we talked a little bit about this on Friday after our matrix quiz, so we'll kind of breeze through special right triangles. You need to know the side lengths for special right triangles. Okay, so I've got 1, 45, 45, 90, and 1, 30, 60, 90. Now, on Friday, when you guys did this for me, you guys gave me sides with x's in them. Okay, so you told me in the 45, 45, 90, it's x, x, and x square root 2. And in the 30, 60, 90, across from 30 is x, across from 60 is x square root 3, and across from 90 is 2x. Some of you might be working on the extra credit sheet that I gave you on Friday that's due tomorrow at the beginning of class with work. I am going to make a little side note here. If you want extra credit. If you don't want extra credit, you don't turn it in, and I won't give you any. Fair. I'm just going to make a quick side note that's going to be helpful as you progress through the chapter and also through your math classes, pre-calculus, etc., calculus. So I'm going to draw another version of each of these triangles. And your algebra teacher may have shown you this. Another way to label those sides without these x's is just by like the coefficients, because it's really like how they're related in terms of ratios. So what's the coefficient to these x's on the 45, 45, 90? 1. So you're going to see me draw this triangle a lot, 1, 1, square root 2. It's the same thing as x, x, x square root 2. I just don't have all the x's. I don't need them. Okay. And on the 30, 60, 90, I'm going to draw it 1, square root 3, 2. So I'm just focused on the number values. I don't really need the x's always. Have you ever seen it written like that? Or do you always put the x's on it? One person is saying they've seen it both ways. This is really nice when you're trying to find side lengths. This is nice when you're trying to do trig ratios. Okay, so it just kind of depends on like which way I like to write it. Okay, so here's two problems, two special right triangles. You can sketch them in your notebook. And then have a conversation with your group. How do you think think you go about solving for the x's that I've labeled? Using that previous slide.
So then the other one would be I would just need to find out. And then so for 0.5,
So, what's the first one? What's the next one? So 30 back and 90. Oh, I mixed up that. So we'll get the second one.
Oh, I did it the wrong one.
You could do that, however, can you use the knowledge about special right triangle and just split up? That's what Okay, as I'm walking around, some good conversations. Now, one thing that came up was using your trig ratios, which, I mean, yes, you could use the trig ratios. The sine of 30 is equal to x over 15. However, if you then do that in your calculator, you won't get an exact answer, or you might get an exact answer in this case, but you won't always. So what I want you to do here is focus on special right triangle relationships. So I heard a lot of people say stuff about 15. 15 is the hypotenuse. In the special right triangle 30, 60, 90, you would label the hypotenuse as 2x. So 2x is 15, which means that x is 15 halves or 7.5. Extra something on there that makes it look like a negative. Either one of those is fine because they're both exact. And x would be the short side. So do you have what you want? Yeah. X equals 7.5. If I had wanted that longer leg, we'd have to take 7.5 times the square root of 3, or 15 halves times the square root of 3. Yeah, we got what we wanted. So now apply that to the 45, 45, 90 triangle. The side that's labeled is the hypotenuse. How do you label the hypotenuse in a 45, 45, 90 triangle? X square root 2. So that's saying x square root 2 is equal to 12. Now, you can answer this a couple of different ways. Some people might be able to just think about what number multiplies with square root 2 to give me 12. If you can come up with your answer right then, fine. If you don't know, divide by square root 2. You get x equals 12 over square root 2. Of course, rationalize that denominator. So we get 12 square root 2 over 2, which is 6 square root 2. So my two sides, two legs, equal measure, are both 6 square root 2. Okay? So that's what I want you to do. There'll be a couple problems on your homework assignment. That's what I want you to practice there. Okay, now you can decide what of this part you want to put into your notebook. However, I recommend everybody at least jot something down about trig ratios for special angles on page 463. And so this table can be found on 463. My hope at the end of chapter 9, if someone came up to you in the hallway and said, what's the cosine of 60 degrees? You would simply say very quickly, square root 3 over 2. Or sorry, it's 1/2. 1/2. Did I say 60?
Yes.
Cosine of 60 degrees is 1/2. And if someone asked you, what's the cosine of 30 degrees? You would say, square root 2 over 2. So the way that you'll get better at that is that you practice it. And it doesn't matter what size triangle it is, so it doesn't matter what the x value is. If it's 1, if it's 2, if it's 3, it doesn't matter the ratio for sine, cosine, and tangent because it will always simplify. It will always be the same value for 30, 60, and 45 degrees. Okay, no matter what size triangle it is, if it's a special right triangle. So I put up here, when you're doing trig ratios, notice I didn't put the x's. Because it doesn't matter what the smallest sides start out as. If I reduce them, they're going to come out to this ratio, 1, 1, square root 2, and 1, square root 3, 2. So I could do the 6 trig ratios for 30 degrees. The sine of 30 is 1 over 2. The cosine of 30 is square root 3 over 2. The tangent of 30 is 1 over square root 3, but then I have to rationalize that. So I get square root 3 over 3. And then cosecant, flip my sign, that's 2. Secant is going to be 2 over square root 3. But of course I have to rationalize that by multiplying by square root 3. So that's going to be 2 square root 3 over 3. And the cotangent is adjacent over opposite. Adjacent is square root 3, opposite is 1. The reciprocal to square root 3 over 3 is just square root 3. Now, at this moment, those things are not clear to us. We haven't practiced them enough that we would know them. But again, my hope at the end of chapter 9, at least the basic ones, sine, cosine, tangent, you just rattle off. You know, it's always going to be that thing. It's never going to change. And you can make a table for 45. For the sine and cosine of the 45, so like if I did sine of 45 degrees, that's 1 over the square root of 2. But I have to rationalize it, so it's going to be square root 2 over 2. Same for cosine, square root 2 over 2. Your tangent is opposite over adjacent. That's 1 over 1 or 1. If you were to do the cosecant of 45 degrees, you'd just be flipping this 1 over square root 2, hypotenuse over opposite. So it's just the square root of 2 over 1. I'm going to get square root 2, square root 2, and 1. And last one there is 60. Well, for the 60-degree angle, you go back to the 30, 60, 90 triangle, so you're going to see some similar values, but things are going to be flip-flopped, right? Now you're looking at it from a different angle. So in the 30-degree, 1 was opposite, square root 3 was adjacent. In the 60 degrees, that flip-flops. Square root 3 is opposite, 1 is adjacent. So my sine is going to be square root 3 over 2. Cosine is 1 over 2. And tangent is square root 3. I already know what the reciprocal of square root 3 over 2 is. It's 2 square root 3 over 3. 2 and square root 3 over 3. Now, there's not a lot of practice with that on your homework tonight. If you look at your gold sheet, I think it's Wednesday, maybe that I give you like a half sheet with practice. So you'll get an opportunity to practice these trig ratios with special angles, I think on Wednesday. But like these values are the only values you ever get for 30, 60, and 45 degree angles. They never change, no matter what the size or the orientation of that triangle is. If it's 30, 60, 90, if it's 45, 45, 90, it's always that thing. Okay, your homework assignment.